Okay, we're going to pick up where we left off on the last video. We're working our way through section 6.3, where we're talking about binomial random variables. In the previous example here, we had just been introduced to the calculator command binomialcdf. That is used exclusively when you are asked to calculate the probability of a binomial random variable that equals a specific number, okay? No less than, no greater than, but equals a specific number. And so we had talked about this example where it mentioned that a basketball player has a 60% chance of making a free throw. I believe they were shooting 10 free throws, and we had established that it was in fact a binomial random variable, and we'd calculated the probability of that particular player making 6 free throws to roughly be, around 25.1%. We did it with the formula, then we did it with the binomial PDF feature. Okay, where we kind of left off then was this table that was created for you was actually created by repeatedly using this binomial PDF feature with at 10 as the number of trials, 60% as the probability of a success, and then this number here, the number of successes, kept getting swapped out for a 0 and then a 1 and then a 2, all the way up through the odds of making all 10 free throws, and that is where these probabilities came from. Okay, those probabilities were then put into a probability histogram here. And then we're going to take a look at this table to see if we can answer this question, finding the probability that she would make at least 5 free throws. Okay. Now please keep in mind, at least technically means the probability that she is making 5 or greater free throws. Okay. So that is actually making 5, 6, whoops, that should be plus 7. Okay, you get the idea, all the way up to 10 free throws. Okay. Now, what I could do, since these probabilities are provided here for us in the table, is I could just add up those probabilities together. Okay, summing up all of those numbers, I would get the answer to be roughly, we're looking at 83.37%. Okay. Now, that was easy because this table was provided for me. Okay, if the table wasn't provided, and remember how I got these numbers, is I repeatedly used binomialcdf on the calculator to get each of these separate probabilities. Okay, this is where what would be actually helpful is a different feature on the calculator called binomialpdf. Okay, now there is a big difference here between binomial PDF and binomial CDF. The PDF, remember the P stands for precise, that can only be used if you are finding the probability for one specific value for that random variable. It has to be an equal sign. A CDF, the C stands for cumulative, and that only works as a less than or equal to probability. Okay, so we just want to make sure that we're keeping this in mind here. Binomial CDF will calculate the cumulative probability starting at where x equals 0, and then it includes all the way up to the number that you would be putting after this less than or equal to. Okay, it works as a less than or equal to symbol. Okay. So the inputs are the same. It has to be the number of trials, probability of success, and what you place here for the x is what you're wanting to cumulatively count from 0 all the way up, including that number you put there. Okay, it's located with second distribution feature on your calculator, and it's option B, so you have to scroll all the way down. You'll see binomial CDF. Now let's talk through how we could use the binomial CDF feature to actually have calculated this probability. Please keep in mind, we were talking about that 10 was the number of free throws. That was the number of trials. She was a 60% free throw shooter. That's the P. Okay, so if we were going to find the probability that she is making at least 5 free throws, here's the trick. This formula only works as a less than or equal to. Okay, and if you look, we're wanting to calculate a greater than or equal to. And so we have to kind of rework this a little bit and say, well, if I want everything greater than or equal to 5, what I wouldn't want, I'm going to use the table here as an example, what we're not wanting to count is everything that is 4 or less than 4. Those are the pieces we're wanting to omit, okay? And so the way that we would want to write this is we would want to say 1 minus the probability of everything less than or equal to 4. Okay, if we were to do that, that would leave us with everything that is greater than or equal to 5. Okay, now thinking through this feature right here, see how that's a less than or equal to? That is where I could replace that with the binomial CDF. Okay, so I'm going to do binomial CDF. Again, I need 3 inputs, N, P, and what I'm counting all the way up to. Okay, so there are 10 free throws, 60% free throw shooter, and keep in mind when I put a 4 here, this is going to calculate the probability of everything from 0 all the way up to 4, the less than or equal to 4, and that's the part I'm wanting to subtract off of 1. Okay, if I were to type that into the calculator, you would get, you can see virtually the same exact answer that we got when we pulled those numbers from the table, 83.38% there. Okay. Okay, so on the next page, we're going to look at an example here called free lunch. Okay, just have as a refresher at the top, you can see that this is our calculator feature that works only with a less than or equal to sign here. Okay, it says suppose that a local restaurant is running a draw an ace, win a free lunch promotion. When approaching the cashier to pay for your meal, the cashier shuffles a deck of cards and asks you to pick a card. If you draw an ace, you get a free lunch. Suppose the restaurant gets 250 customers on a given day. Find the probability that they give out 25 or more free lunches on this day. Okay, before you get too ahead of yourself, and I know that this section is all exclusively on binomial random variables, but on the AP test, you're going to be given a random assortment of free response questions. And nowhere in this problem did it mention anything about this necessarily being a binomial situation. So you need to train yourself to first think through, before I jump to using a binomial command on the calculator, I need to confirm that this situation is in fact a binomial situation. And so we just want to kind of run through here, what is a success and what would be defined as a failure. And in this particular setting, a success would be if the customer drew an ace, a failure would be that they did not draw an ace. Okay, as far as independence goes, the act of shuffling the cards in between, the shuffling is representing or represents independence, where each trial, each customer that comes up to draw an ace, whatever happened previously, the next customer, it's completely independent of that. Okay, the N, we're talking about there being a total of 250 customers, and then we want to know what is the probability of a success. So this would be the probability of selecting an ace. We know that a deck has 52 cards. There are 4 aces in that, so in essence, basically we have a 1 in 13 chance of getting a success. Okay, so this has proven that this is actually a binomial scenario, so we can go ahead and move forward with using that to kind of calculate the probability here. Okay, we're looking for the probability they give out 25 or more. So I'm going to put x is greater than or equal to 25. Okay, please again keep in mind the CDF feature only works as a less than or equal to. So if your problem is a greater than or equal to, you're going to have to use kind of the concepts of complements, that if we want to count 25 or more, then what we're not wanting to count is 24 or less, okay? And when you write it like this, now this is a less than or equal to, so now I can replace this part with a binomial CDF command, okay? So I'm going to replace that with binom CDF. I need to label my 3 calculator inputs, number of trials, probability of success, and then my last number is what I'm wanting to calculate the probability from 0 all the way up to, okay, which in this case would be the 24. Okay, so we're going to say there are 250 trials, that's the 250 customers. We said there was a 1 in 15 chance here of, 1 in 13 chance of selecting an ace, and we want to go all the way up to 24, and that's what we're subtracting off of 1. Okay, if we type that into the calculator, we get the probability of having 25 or more customers to be 10.8%. Okay, by the way, we certainly, for a problem like this, would not want to use the binomial formula that's on the formula sheet. That actually works just like the PDF feature on the calculator. It only is calculating one probability, and if you were to try to use that for this, you would have to use it so many times. You'd have to calculate for 25 successes, 26 successes, 27 successes, all the way up to 250 successes. You'd have to repeat that formula that many times. So this is hands down, you definitely want to use this binomial CDF feature here. Okay, looking at this next example, this is really going to unveil what will prove to be a very, very important condition that we need to know and use for many future chapters here, particularly in the latter half of this year. So this is looking at, you have cereal box companies all the time that kind of run these promotions where they have different things in the box that you're trying, like collectibles. This is saying that a cereal box company is putting 1 of 5 different cards into each box of cereal. It says each card features a different NASCAR driver. We have Jeff Gordon, Dale Earnhardt Jr., Tony Stewart, Danica Patrick, and Jimmy Johnson. Suppose that the company printed 20,000 of each card. Okay, so we're looking at there being 100,000 total boxes of cereal that have 1 card inside. Okay, if a person bought just 4 boxes at random, we're going to let X, our random variable, be the number of cards that would feature the driver Danica Patrick. The first question A here says, explain why this is actually not a binomial setting. Okay, so we can see here it certainly feels like, you know, it's binary. The success would be getting a Danica Patrick card, and a failure would be not getting a Danica Patrick card. But when we get to the I, that's where I think we run into trouble with the independence feature for this, because when you go buy that first box, you're not going to replace that box, like return it, when you go buy your second box. So it feels like here maybe the independence condition, okay, the independence condition is being violated. Okay, we're going to say it is violated, and how it's being violated is basically due to not replacing the boxes. Like, we're not replacing them in between selecting them. So if we buy one of the 100,000 boxes, when we go to buy the second one, now there's only 99,999 boxes left to choose from. And when we go buy the third box, there's 1 less from that. So it feels like the probability of a success is changing because we have less to choose from because we're not replacing those boxes. And realistically, in this scenario, it makes no sense. No one would be replacing a box of cereal that they have already opened. So this is asking us to calculate the probability that you would get no Danica Patrick cards. Okay, so we're looking at the probability that X would equal a 0. Now remember, this is not a binomial setting according to what we said here because the independence condition is not being met. So I cannot use the binomial formula, I cannot use binomial PDF. I'm simply going to use just this concept of probability that when I choose the first box, okay, I choose the first box, if I'm talking about not getting any Danica Patrick cards, keep in mind they said they printed 20,000 of each driver's card. So if the first box I purchase is not a Danica Patrick card, that means 80,000 of the 100,000 boxes. That's kind of what the odds of that first box not having a Danica Patrick card in it. Okay, well now my denominator here for the next fraction is going to be 1 less than 100,000 because I have one less box to choose from. And assuming that I didn't get a Danica Patrick card on that first box, now there's only 79,999 cards that are not Danica Patrick cards. So you can kind of see the pattern here. I'm going to follow through. I'm going to reduce my denominator by 1, and I'm going to reduce the number of non-Danica Patrick cards by 1 as well, until I'm showing this fraction 4 times, representing the 4 boxes of cereal that I have purchased. Okay, and if I multiply those together, I get the likelihood of me selecting 4 boxes of cereal and none of them having Danica Patrick cards to roughly be about 40.96%. Okay, now here's the interesting thing about this particular idea. Okay, we do typically say that in general, this notion of without replacement, which is what I was doing when I was picking 4 boxes of cereal and not replacing in between each selection, we normally do say that that is certainly a violation of the independence condition. However, we have a condition called the 10% condition, okay? And what the 10% condition basically says is if your sample size, that's what this lowercase n is, if your sample size that you're choosing from your population, and we're letting capital N represent the population size, okay, and you're selecting without replacement, okay, so we're talking about this scenario here. Lowercase n is our sample, capital N is our population size. If your sample size is under 10% of your population size, then technically we can still say that even though the independence condition is not being met, it's not going to have that much of an effect on what the binomial probability calculation would have been. Okay? So in other words, your sample size has to be 10% or less than the population size is. And if that's the case, even though you're not doing replacement in between your selections, the independence condition is actually not being affected very much. And I'm going to show this to you with this Danica Patrick example. Okay. Now, what has to be shown first, and you have to do this on your homework, you have to show if it is a problem that you are not replacing in between your selection, you have to show that this 10% condition is met before you can jump over and use a binomial calculation to calculate the probability. My preference is to use, these two things up here are actually just two different ways of saying the same thing, but I like this feature a little better here. Okay, what we would need to show is you would need to show that if you took your sample size and you multiplied the sample size by 10, that is still going to be a small enough part of your population that it's not going to be very impactful. So in this example, our sample size was 4 boxes of cereal and the population size was 100,000. So I'm going to plug a 4 here and I'm going to plug a 100,000 over there. Okay, and if I work this out, I get 40 on the left. If this comes out to be a true statement, and obviously 40 is well less than or equal to 100,000, I have shown that this 10% condition is met. That means I can move over here and say, okay, well, I'm going to go ahead and use binomial PDF. Okay, it's a PDF for the reason that this is an equal to here. Okay, I need 3 inputs, the number in my sample, which is 4, the probability of a success. Okay, remember the probability of getting a Danica Patrick card is 20%. Okay, 20%, and then what I'm calculating is 0 successes, okay, that there are no Danica Patrick cards. If I type that into the calculator, you'll notice the answer that we get for this was in fact the exact same answer that we got over here when we worked the problem out as if it was not even a binomial random variable, okay? And the reason this came out the same is because the sample size was so small that despite the fact that we weren't replacing the cereal boxes, it didn't really impact the fact that the independence condition was not being met. Okay, so we're going to look at one final example here where we get to kind of run through whether this 10% condition is met or not. It says, suppose that 10% of CDs have defective copy protection schemes that could actually harm computers. A music distributor inspects a simple random sample of 10 CDs, so that's my sample size, my lowercase n, from a shipment of 10,000, that's my population size, capital N. We're going to let X represent the number of defective CDs. Okay. Once again, I'm going to run through and confirm that this is in fact a binomial setting. A success in this case, remember, success doesn't necessarily mean good. Okay, we're letting X be the number of defective CDs, so a success is actually a defective CD, and a failure would be a non-defective CD. Okay, now for the independence condition, clearly when this distributor is picking 10 CDs from the 10,000, it stands to reason he's not throwing the first CD back in and then reselecting. He wants his 10 CDs to be 10 different CDs from this 10,000 population. So he's not going to be replacing it, but if I can show that the 10% condition is being met, then that means this independence condition is still being met. Okay? When you show this, you're going to show 10 times your sample size is still under or equal to your population size. Okay, so you're just going to show that substitution and show what you get here. We certainly would say 100 is less than or equal to 10,000, so we can keep moving forward here with that independence condition. Okay, the number of trials, that's the number in the sample, is 10, and the probability of getting a defective CD, I told you up here, 10% of the CDs are defective, so that's 0.10. Okay, so I can go ahead and move through here and find the probability that there are no defective CDs at all in this particular sample. Okay, now if I were to use the formula on the formula sheet, this is how I would set it up. Okay, if I were going to use the formula. And there are multiple choice questions that involve the formula. So you don't always want to use the calculator command. Make sure that you're really comfortable with using the formula as well. Okay, we had talked in a previous video that to get this binomial coefficient here, you have to use the NCR feature, which is under the math button under the probability menu. Okay, 10 would be your N and 0 would be your R there. Okay, you could type it in that way, or we could do binomial. This is a PDF because it's an equal to, okay, not a less than or a greater than here. Okay, we label our inputs. There are 10, 10%, and a 0, and either way, we're coming out with 0.3487 as our answer. All right, few problems there.